Hey everybody. Today we're going to talk about applications of a normal distribution. Before we get started, I want to point out that in the TI, to get to a normal CDF, you're going to go to distributions, which is above the vars button. So second distribution. And we're going to be using a normal CDF as well as inverse norm here. Now there are two interfaces. One of them does this. And the formula is here. It's the lower bound to the upper bound, then the mean, and then the standard deviation in that order. This is for older TI 83s and some of the TI 84s. For the newer TI 84s, we go to distribution. And when we go in, we have a completely different interface. So it's again lower, upper, mean, and standard deviation. I will be using this format for the duration. For a Casio, it's actually, what you have to do is we're going to go to options. Then we need more options. Then I go to probability. That's not right. Options, stat, and distributions. And here's my normal distribution. And here's my norm PDF, CDF, and inverse norm. And the Casio, you can just keep those up there. The biggest difference with the Casio is that these are switched. For a Casio, it's sigma, and then the mean. Once again, this is for the Casio. With that said, moving forward, I'm going to use a TI for most of these. And we're going to start with standardizing a normal random variable. What we do to get the standard normal is we convert it to a z-score. And if you remember, a z-score is the number of standard deviations away from the mean something is. So if the z is 1, that means it's exactly 1 standard deviation away from the mean. We're also going to be talking about area under the curve as a probability. We've already done that in a previous lecture. And we're going to, in a standard normal, mu is 0 and the standard deviation is 1. And by the way, for these here, we don't even have to put those on there when it's the standard normal. When it's a 0 and 1, the mean is 0 and the standard deviation is 1. We don't need to put those last two on at all, only if it's not that, which this first example will not be. So let's practice. So we assume that a drive-through times at a local burger place are normally distributed with a mean time spent in the drive-through of 138.5 seconds and a standard deviation of 29 seconds. So right off we can see that we have mu is 138.5 seconds and the standard deviation is 29 seconds. Well, what we can do is we can actually draw out a little picture for us. What is the probability that the randomly selected car, that any randomly selected car, will get through the drive-through in less than 100 seconds? So I'm going to draw this out a little bit. And in the middle goes the mean. This is seconds. And 100 seconds is definitely less than the mean, so we're definitely over here. Let's say we're about here. So less than 100 seconds is going to be there. And we want to know that probability. Well, we can see right away that this is norm CDF. Where the lower bound is a really large negative number. So I'm going to go negative 99999. Doesn't matter how many nines, as long as you have a bunch. And that's going to go up to 100. Now you can see that the mean and standard deviation are not the standard normal, so I'm going to have to put those in. And once again, I'm going to let my calculator do the heavy lifting here. Normal CDF, here, let me show you again where that comes from. Go to distribution. Let's go over here. So second distribution, my normal CDF. And again, it's lower bound, which in this case is negative 99999, doesn't matter how many, up to 100, with my mean 138.5, and a standard deviation of 29. And the calculator does all the heavy lifting for me. So what's the probability that a car will get through in less than 100 seconds? Not too high, a little over 9%, which makes sense. So same scenario. We have to go too high there. What is the probability that a randomly selected car will spend more than 160 seconds in the drive-thru? Well, once again, let's draw our and they want to know more than 160 seconds. Well, 160 is on this side. This is 160. So, once again, this is going to now start at, my lower bound now is 160. My upper bound is just some big number, with a mean of 138.5 and standard deviation of 29. Once again, second distribution, normal CDF. Now it's 160, do a big number, with 138.5 and 29. In this case, there's a higher probability that it will take more than 60 seconds than the probability of less than 100 seconds. Finally, for this one, what proportion of cars spend between 2 to 3 minutes in the drive-thru? I want to point something out here. We need to be extra careful. They gave this to us in minutes. All of our other ones are done in seconds. So I'm going to convert 2 minutes is 120 seconds, and 3 minutes is 180 seconds. So once again, I'm going to draw my fancy picture here. Ooh, not so nice on that one. 138.5. And 120 minutes is over here, and 180 minutes is going to be over here. And you can see this is going to be the vast majority of these. And this is 120, 180. So we're going to have norm, CDF of 120 to 180. Mean is 138.5, standard deviation is 29. And 29. So this comes out to be about and as expected, the majority of the probabilities are between 2 and 3 minutes, or 120 seconds to 180 seconds. So we have over 66% chance that the stay will be between 120 seconds, 180 seconds. So here we have a new one. The reading speed of 6th grade students is approximately normal, with a mean speed of 125 words per minute and a standard deviation of 24 words per minute. So once again, our mean is 125 and a standard deviation of 24. What is the reading speed of the 6th grader whose reading speed is at the 90th percentile? So we need to set this up very carefully. If you remember, a 90th percentile means that 90% of the students are below this particular student. What that means for us, again, our mean goes in the middle. 90th percentile, that is definitely going to be way over here, because 90% of the information, 90% of the students are going to be slower readers than this one, which means the area in here is 0.9. We are going to now use inverse norm because we want to know the number of words. So these are words. So if you remember, inverse norm means area to the left, which very nicely that works out for us. So again, distributions, inverse norm this time. Inverse norm is going to be 0.9 is the area to the left, comma. Mean, once again, 125. Standard deviation is 24. Again, in the Casio, those are switched. So what are the number of words per minute that a 90th percentile student would do? About, let me write this out. That is going to give us about 155.76, we'll say, words per minute. You can see that's quite far away from the mean. We'll say 156. Round that off a little bit. Not too bad. So we're still based on the reading rates of the students. And we're going to determine the reading rates of the middle 95% of all 6th graders. And then what are the cutoff points for the unusual readers, both slow and fast? If you remember, the mean was 125, standard deviation was 24. Middle 95%. Well, so if we have the middle 95%, that tells us that what's left over here and here is the remaining 5%. And half of 5% is 0.025%, called the two-tailed. And once again, we have area to the left, so we are going to have inverse norm. Area to the left for this first one here is going to be 0.025, the mean and standard deviation. And that gives us 77.96. Again, these are words. For the second one here, how much area is to the left? Well, that's going to be 0.95 plus 0.025. And you can put it in the calculator like that as well. I will show you. So we have 0.95 plus 0.025, comma, 125, comma, 24. So here are the cutoffs. Meaning if there's a student that reads less than 70, we'll say 78 words per minute, they're considered a little slow. If they can read more than 172 words per minute, they're considered to be more advanced. Moving on to the percentile. So we have 20th percentile, and once again, percentile means area below. And since it's area to the left, that's going to be over here, because this is going to make up, outside the lines there, 0.2. So once again, that cutoff is going to be inverse norm. 0.2, 125, 24. Oh, I did that wrong. 0.2, comma. When you don't put the standard deviation or the mean in there, then it assumes that it's a 0 and a 1, and it definitely isn't in this case. So if a student can read 104 words per minute, 105 words per minute, then 20% of the other students read slower than that particular student. Here we're finding the third quartile. And if you remember, the third quartile means that 75% of the information is below. Here we have 0.75 is what third quartile means. So once again, inverse norm. 0.75, 125, and 24. .19, we'll say. So again, these are words per minute. 141.19 words per minute. All right. Suppose X, the grade on a midterm exam, is normally distributed with a mean of 70 and a standard deviation of 10. The instructor wants to give 15% of the class an A. What cutoff should the instructor use to determine who gets an A? Well, once again, there's a handy dandy graph here. Mean is 70. So once again, we have our mean, 70. Standard deviation is 10. So the top 15% is going to be over here somewhere. Once again, to be clear, these are scores. And in here is 0.15. Now remember, inverse norm only knows area to the left. So the area to the left isn't going to be 0.15, that's area to the right. So we're going to do the complement. And once again, we could just put that directly into the calculator like that, as I will demonstrate. One minus 0.15, mean is 70, standard deviation is 10. So that gives us 80.36, we'll say. So anyone for this particular class that scored 80.36 or higher automatically is going to get an A, according to this teacher.